Folks, if you can get seated, we can get the session going. All right, so we have three interesting talks, and it turns out that for actual system performance, more than microarchitecture, platforms matter. And our first talk is on that front on CXL by Mohan, and he's at HPE, and he works primarily for the last 25 years, as I read from his CV, on platform architectures, and there's a lot to do, and probably not as well studied in academia, in my opinion. And so it's a great opportunity for all of us to learn a little bit about what the CXL architecture does, and that will be Mohan's responsibility to teach us.
Thank you, sir. So, welcome everybody to this talk. I know it's the first session after lunch, so it's going to be difficult on both of us, and I'll try to make it as interesting as possible. I realized that I didn't say what CXL is, but from Mark's session in the morning, I think everyone knows what it is about, so that's something I don't have to really tell. But at the same time, I will try to introduce from the beginning and the motivation for it, so that you get an idea of what it is about. I also noticed that in Krishna's talk, the last slide was a Calvin and Hobbes cartoon. I'm a huge fan of Calvin and Hobbes, and I feel at some point of time maybe Calvin would have been a computer science student, maybe at IISc, seeing some of the quotes which come. So you will see a few of them sprinkled in between the slides. I hope it will keep you awake also as we go through this. So the agenda for this talk today, I'll start with the motivation for CXL, talk more about the technology and what has been happening over the last few years with the specification. And then I'll go into the hardware software ecosystem. Like Professor Murli was saying, I think it won't be an academic background as much, even though I labeled the talk as research to reality, and that's what I wanted to talk about. It's more like from reality to research, in my opinion. You will see that I'll be talking more about what's happening in the industry, and then go to the last part where I'll talk about what's happening in academics, which is kind of probably going to be the next stage of reality. So that probably is more apt. So it's probably called from reality to research. So yeah, the motivation for CXL. So why do we need another fabric, right? I think like I was asking Mark in the morning, if you see on the fabric side, there are so many of them. It's like an alphabet soup which is coming up. Everyone wants their own fabric. So CXL is one such new fabric which has come up. So we will talk about what is the motivation for CXL and why it is getting popularity. So if you see, again, a lot of this, I think Mark set the stage in the morning, so I don't really need to go into too much detail. But as we all know, Moore's law has been declining. Dennard scaling has almost died in a sense. And so what has happened for that is that the number of cores per socket per CPU has started increasing at a phenomenal rate. And so this is a bit of an old slide. It shows 64 plus cores. It's gone much higher now. If you see, for instance, there are CPUs with 200 plus cores out there. And once we have that kind of situation, they are all again like Krishna's grandpa and his workers, right? These are all the workers who are again looking at that memory and trying to see that how they can get enough bandwidth out of the memory. And so the bandwidth per core naturally has started dropping, and memory technologies have not been able to keep up with that. So for DDR, for instance, today on the system we have 4,000 plus pins for DDR. That's a huge number of pins. So it's becoming more and more difficult to create sockets which have that number of channels which are there. We used to have typically around 6 channels. We got 8 channels at some point. Again, it dipped to 6. We'll probably have 12 channels coming up with some of the CPUs going forward. But then it's becoming a huge challenge in terms of putting multiple of these DIMMs also per channel. So we support 2 DIMMs per channel today. But going forward with higher speeds greater than 5600 megahertz, for instance, I don't think you will be seeing 2 DIMMs per channel. You will typically see just a single DIMM per channel, which means you are constrained by capacity when you're trying to go higher on bandwidth. So these are some of the challenges which systems are facing today, right? So if you go to higher capacity DIMMs like 256 gigabyte DIMMs or DDR or HBMs, you will require the 3D stacking, which again Mark talked about in the morning with the TSV kind of technologies, and that's hugely expensive. So it's a big challenge for the community, the server vendor community, to figure out how to handle these, along with the processor vendors to figure out how to handle this. So this is something I would like to think that HP kind of thought about it. Probably one of the first around in the last decade, where we came up with the concept of the machine and the memory-driven computing project, where we said that instead of having things oriented around processors, each of them talking to memory and then talking to each other over an interconnect, why can't we have memory at the center of things and all processors and accelerators talking to memory? So that's where the Gen Z protocol came up, which was, I think, the beginning of some of this memory semantic fabrics. And by memory semantic fabrics, what I mean is a fabric where you can actually do load store to it. It is not something like a PCIe where you have to do a producer consumer model and then have a DMA which is happening, which is also non-coherent. So this is a coherent kind of load store kind of semantic fabric. So it's almost like accessing memory on the DDR bus on the system. But Gen Z didn't really take off. It is something which, as you can understand, I think this requires the processor vendors to be completely bought into the spec. And Gen Z required a huge change for processors to integrate it into them. And so I think around 2019, the CXL consortium was incorporated and the CXL 1.0 spec came out. CXL is pretty much modeled on the lines of Gen Z, but it takes care of that compatibility issue by being layered on top of PCIe, which is already a standard. So we've seen CXL go through multiple iterations from the 1.0 in 2019 to the 3.0 in 2022, which it shows here. This year, soon you will have the 4.0 spec coming out. I am not sure if it has yet been released. Probably it will be coming out in a few days or so. So it has been developing almost at a really breakneck speed kind of thing. Every year we've been seeing a spec come out, and it has been tough for vendors to kind of keep up with it. But we are now seeing vendors really coming out with devices based on CXL, and I'll talk more about that as we go forward. So again, introduction to CXL. Like I said, so many of these technologies coming up. There are 3-letter acronyms, 4-letter acronyms, and things like that. Of course, I think we don't know how to name some of these technologies, but yeah, that's another point. So what is CXL? So CXL, like I was saying, it's a memory semantic fabric, which means you can do load store over it. It is layered on top of PCIe, so it uses standard PCIe technology at the physical layer. It uses what is called a flex bus post. So if you have a server and if you have a CXL slot, it can talk both PCIe and CXL. It will come up initially at PCIe Gen 1 X1 with a lane 1, and then it will transform to CXL if a CXL device is connected on that. So that makes it very, very flexible for people who are using CXL. And again, Mark was mentioning this in the morning. So it is not something which is going to go waste, saying that, oh, this has been kept aside for CXL and so nobody else can use it. It is something which is PCIe at its core. It can be used as a PCIe device, but today PCIe devices slots are lying vacant on the system. So this gives a dual benefit of having more utilization of the slots and being able to use them for CXL and attach memory to it. So I'll come to how that attaching to memory comes. So CXL has 2 ways that you can actually connect devices to it. So one is the standard PCIe way of doing it. That is, you have an add-in card or a chem form factor as it's called, or you can have a typical EDSFF backplane into which you insert the EDSFF E3.S kind of drives. So you can insert a CXL drive into that bay. So you can get both those kind of devices on a system, and it can support memory on it. Again, more about it in subsequent slides. I talked a lot about this. So CXL 1.1 was layered on top of PCIe Gen 5. 2.0 again was on 5. What CXL I think has coincided with like the other fabrics which have started coming out, and the rise of AI, right? So the challenge has been that the bandwidth is never sufficient, which is there. I mean, with some of these technologies. So PCIe has gone through a real fast cycle in terms of new versions coming out just to meet the or come close to the bandwidths of something like an NVLink, for instance. So we have seen 5, 6, and 7, and even 8 getting announced very pretty close to each other. CXL 3.0 is based on PCIe 6, and the 4.0 one, which you will see coming out now, will be based on PCIe 7. So that's really fast progress in terms of the specification, just to keep in touch with what's happening on the AI side of things. So an example of this speeds and feeds on the in the table. You can look at it afterwards to get an idea of how that matches up with NVLink and other technologies. But what about the protocol? So like I said, at a base layer, it is layered on top of PCIe. So the physical layer is PCIe, but then you have the other layers on top, the protocol layers, where you have the CXL differentiation. So CXL itself has 3 sub-protocols within it. So one is CXL.io, which is pretty much PCIe in terms of discovery and all those things which are required for PCIe. And then there is CXL.cache, which is for caching, and CXL.mem, which is for memory accesses. So I'll again talk a bit more about that in the next slide, I think. Yeah. So based on these 3 protocols, that CXL.io, CXL.cache, which supports caching, and CXL.memory, which supports memory expansion with CXL, there are 3 types of devices which CXL can support. There's a type 1 device, which is basically just a device with cache on it. And what it means is it's an accelerator with cache, for instance, so it can access memory on the DDR, for instance. It can cache it within itself, so it participates in the coherency protocol of the processor. So this is something which is again, there are probably no devices out there today which only support this CXL.cache, but it was seen as something which would be useful for the partition global address space kind of NICs which are used in high performance computing, because you can do NIC atomics. So you can do atomics with this kind of protocol being supported. Type 2 is the second one. Interestingly, it is not a gradation, right? You would think that type 1 is cache, means type 2 has maybe one more protocol added or something like that. But interestingly, type 2 supports all 3 protocols. So it is IO, cache, and memory all supported on a single device. And here the benefit is that the accelerator can not only participate in the caching protocol, it can also have its own memory or HBM, DDR or HBM on it, which it can export to the system, to the processor. The type 3 device is the one which has gained the most popularity over the last few years, and I think it's where devices are coming out today. For type 2, I think there's probably no production device out there. There are a couple of people who are looking at it, and I'll talk a bit about that later. But type 3 is where there has been the most interest, and most other vendors have started playing in it. And what it allows you to do is that it allows you to expand the memory in a system. So instead of just having the DDR memory bus or channel on which you access the memory, now you can have additional memory on a system by putting it on the PCIe or CXL bus. And this allows you to expand the memory on the system. And we talked about some of the use cases with AI too, with Professor Murli talked about the KV part of it. So there are advantages which can be made use of by using that CPU's additional memory by the GPU. But to be frank, I think CXL has still not broken into the AI space. I think it's something people are still exploring to see if there are advantages of it. So this, I think, this diagram basically gives you a good idea of what a system will look like, right? With a traditional server, which you would have known in the past, a CPU is connected to memory through the memory controllers, and it's connected to accelerators or devices, NICs, etc. through the PCI bus. With a CXL enabled server now, what you can do is, in addition to connecting the accelerators or the PCI bus, you can connect the CXL devices or CXL memory, in this case the type 3 memory, over the CXL bus. So you are able to expand the memory options on a particular server. So like it says here, the addition of CXL DRAM can provide now double the memory capacity, which may not be literally true. I think it depends on how much memory you can put on a server and how. But the advantage with CXL is that you can expand it outside the box too. So you can actually expand outside the box and make it maybe double the memory capacity if you want. But the bandwidth is it's probably not. It's around the same for DDR5 and with CXL 2.0. So I think it can provide almost the same memory bandwidth for a slot versus a channel. So the evolution of CXL. So I'll now talk about it. So CXL evolving. I think every spec which comes out has tried to address issues which people have raised with the previous version, and so it has been like. It's almost like the transmogrifier, right? Which Calvin talks about, where you say that, okay, what do you want next? Just write it on the site and I will deliver it in the next spec. So that's what has been happening, and it's been happening at a breakneck speed, like I said. So since September 2019 to 2024, I think around now four releases have already happened, and there's a fifth one on the way. CXL 4.0 is on the way. The number of members has also increased and all the processor vendors are part of the CXL consortium, so that's probably a good thing. And you see Intel, AMD and others, everybody engaged in trying to get the next generation of servers with CXL. So what was now I'll go into the each of the specs, I think at a high level, just to give an idea of what was added with each of them, and so you'll get an idea of what are those things that people have been writing on the side, right? So CXL 1.1, I think the thing was, it was basically about expanding memory and expanding bandwidth. So you could attach extra memory to a server, you could give more bandwidth to a server in terms of memory. So both those were seen as the major advantages of CXL 1.1. I think almost no one adopted it really in the industry, even though it came out, because the spec was not fully matured in terms of other features. But what it did is, if you've seen this pyramid which is out there, which shows the memory hierarchies on a system, it now put in another layer in between. So memory has become even more tiered and hierarchical with CXL coming in. And as you will see when I talk about some of the research which is happening, you'll see that a lot of research is happening in this space to see how applications can take care of the fact that there is this different levels of memory with different kind of features and how they can utilize it. So another advantage of CXL. So if you see a standard server, right? I think. Oops. Sorry. It seems to be going forward. Okay, sorry. Yeah. So if you see a standard system, right, you'll have the SoC has a media controller attached to it, and then you have the DRAM attached to it through the memory bus. What CXL has allowed us to do is that it has allowed us to put the memory controller now out of the SoC's control. So the CPU logic, CXL logic, now directly talks like PCIe to the controller, which is on a disaggregated memory module. It could be on the same system, it could be outside the system. We'll come to that. So the use cases, again, I talked about it. You can now expand memory. You can, if you have one of those E3.S kind of drives, you can put it on a drive bay on the system. If you have a PCIe card kind of add-in card, you can put it as an add-in card. So that's kind of the advantage you get. With 2.0, so people started saying, okay, this is not sufficient for me. Even if I add, for especially the hyperscalers, for instance, Google, Microsoft, and others, they started saying, my main problem is memory stranding. the fact that there is memory stranded within a server. So even if I increase the memory capacity within a single server or increase the bandwidth, it's not beneficial to me because not all my data center can take advantage of it. So that's where the pooling use case came, and that is the primary use case of CXL 2.0. What it allows you to do is, first level is disaggregation, which is basically taking the memory outside the system. It is no longer within a single server, for instance. And once it's outside the system, you can assign that memory either to one server or the next or any other server in the data center, depending on how how you can connect it. So now it basically becomes a rack scale. So starting from a single server technology, now it has become a rack technology, where you can, within the rack, if you have multiple servers and if you have a top of rack switch or memory device kind of thing, then you can connect that memory device to all of the nodes. But at one point only one of the nodes will use that memory. You can have orchestration software which will decide, okay, maybe this server is not having sufficient memory right now and this server has too much memory and I can move the memory around. So that was the first use case which people asked for. And so that's what 2.0 did. The other thing it did was, from a device perspective, it allowed people to break it up, saying that instead of having a single logical device, now you can have multiple logical devices. So within a single device itself, you can have multiple logical devices, and then you can assign each of these logical devices to one of the hosts to which it is connected. This allows even more flexibility in terms of actually moving that memory around or assigning that memory around between multiple hosts. So yeah, at a high level, these are the use cases. So in the bottom, you'll see this value prop which I'm putting out there. This is something which Dr. Debendra from Intel, I think, talked about in the CXL DevCon. So each of the value props of each of the specs is kind of put in the bottom part of it. What now 2.0 also allows is, it allows something called a CXL switch. So it's like a PCIe switch. It could be outside the system, and to that switch you can have more memory devices connected. So it really allows you to span out and be able to connect more memory to a set of systems. Then okay, so then people started saying, okay, maybe even this is not sufficient for me. I mean, with memory pooling I can only access one memory at a particular time. A node can only access some memory, and I have to move it between nodes and things like that. What maybe AI use case, it would be good if I could have a shared memory like that, where I can put everything, key values, store or something like that, and then be able to share it between multiple nodes which are out there. So that is where the sharing use case came up, and that was 3.0. So 3.0 allowed you to do sharing. It also broke up a lot of the issues which were there with switches. So PCIe, as you know, is a very hierarchical technology. You can only connect in a tree kind of topology. With 3.0, what it allowed you to do is you could connect it like almost like fabric. You could connect switches every way, which way, and be able to get routing between them through what is called as port-based routing instead of the hierarchical based routing. It also started a concept called fabric attached memory, so which is concept from the sharing use case. That is, now you have a memory out on a fabric and you can access that memory on the fabric. You could now have global fabric attached memory, so everybody could use that memory. Okay, so what's the industry landscape? So like I mentioned earlier, there are slots, add-in cards which you can use. There are these EDSFF kind of drives which you can use. Which one is getting more popular? The drives are the ones people really like, because they feel they can just put it anywhere, they can pull it out easily. It is not like a DRAM or something for which they have to go in and take out the board and then take out memory or something like that. But it has challenges in terms of the amount of power it can handle and things like that. So sometimes an add-in card is more preferred. So we are seeing both of those use cases in the industry today. So this is the ecosystem, high level. So you can see the E3.S memory drives from Samsung, Micron, SK Hynix, etc. And then you have the add-in cards from Smart and Astra Labs, for instance. And then you have these fabric attached devices, right? So you have this add-in card fabric box from H3 and from Liquid. and then you have the E3.S box from Samsung. So it's like the whole portfolio is now out there, but most of it is based on CXL 2.0. There are people slowly moving to CXL 3.0 in the future. In terms of performance, I think that must be an obvious question which you have. What is the latency for CXL? So the latency for CXL is kind of similar to going across socket to access memory attached to another socket. So it is like similar to that NUMA domain. So what you see as a NUMA domain with another socket, you will now see this as another domain. And like Mark was saying, it's called Z-NUMA, which is like zero NUMA because it doesn't have any CPUs attached to that NUMA domain. It is only memory which is attached to that domain. In terms of bandwidth, I think you can get pretty good bandwidth, almost same as DDR today. And with newer versions of the spec, you might get even more. The other advantage with CXL is that it is, because it's layered on PCI, it is bidirectional. So if you have bandwidth where, I mean, if you have applications which are doing both read and write, you'll get benefits of it with CXL as compared to DDR. Okay, now looking at, I don't think I have too much time, so I'll have to rush. On platform enablement, so this is an area I kind of work with closely, that as we are trying to enable it in HPE servers. So we've had a lot of things which you have to enable. We have to, of course, enable the hardware in terms of these backplanes for the E3.S device support. We have to do firmware support in the UEFI, the ACPI tables. There are some new ACPI tables, especially to recognize the NUMA on the system. So there is the HMAT, SRAT and SLIT. The SRAT and SLIT are old tables which used to be there earlier also with the standard NUMA which you get with sockets. You basically know what NUMA node is and what is the CPU attached to it, what memory is attached to it. With HMAT, what you get is you actually get what is the latency of a particular CPU NUMA node to another NUMA node connection and the bandwidth associated with it. So those are things which application developers can use as they go forward. So that is again something which the system firmware has to enable on the systems. Then from a manageability perspective, from a BMC perspective, you have to handle all the things around MCTP, PLDM for sensors and things like that. Software, again, there are a lot of things which need to be handled. So I'll rush a bit. QEMU and Linux have gone through a lot of changes for this. QEMU supports complete emulation of CXL environments, so it's very good. So even if you don't have devices out there, you can use QEMU to do what you want. Okay, I'll move into the research part of it. So there have been a lot of areas in research which people have been looking at of CXL, especially like I said, memory tiering, memory pooling, memory sharing, and then type 2 accelerators is just coming out. I think VMware is one of them which has started looking at it. There have been some interesting Linux kernels, same page merging hardware with type 2, which has been work has just been done in, I think, Urbana-Champaign, I believe. And there are of course some AI inference use cases with GPUs, but nothing from NVIDIA today. So that's one, I think, challenge which is there, or from AMD for that matter. The OCP, there is a CMS academic research work stream which I have been part of also, and there's been a lot of good work happening to see what industry can do with the academic research and how we can take it forward. Again, you can take a look at it in the slides and come back to me if you have any questions. And then these are some of the papers which I put out there to say what has been happening over the last last 2 years or so in terms of CXL papers. Like I said, most of the work is around hierarchical memory and being able to use tiered memory and page migration, cold page to hot page kind of migrations, hot page to cold page migrations. And then there are other things which are now happening around GPU and AI use cases. And yeah, I think just I'll leave you this last slide, which is a plug for a HIPC Fabrics workshop, which I'm the chair for, which is happening in December of this year. So if you want to hear more about CXL, UEC, UAL, and all that, I think you can come and attend this. Thank you. Questions, folks? Mark has a question.
Hi, thanks for the talk. I had a question regarding the interface. All this for the CXL memory. do the programmers have an easy way, programmers in say, if I want to exploit this, right? Is the interface public? Is the support there? And is there and typically what happens in such interfaces when we have questions, we need someone to answer these.
So yeah, I think Krishna, it's a good question. So in terms of CXL, right, it is like a standard memory. So you have it's a standard load store as far as the processor is concerned. As far as applications are concerned, it depends on what the OS does with it. So the OS can present it as user memory direct as its DRAM, and you could use it as if it is DRAM. But then you will have the latency effect. So it is tiered memory. Again, applications know that it's tiered memory. So you can decide whether you want to use this as some cold memory or you want it as your actual application code space or something which you want to access very frequently. So applications can make that decision on how they want to use it, but OSs will present all those abstractions to you.
So the question is this, that do we have simulators like Gem5 and then Fabric where we can simulate this so that we can do some architecture exploration?
There is emulation with QEMU, like I mentioned, right? So with QEMU, you can actually emulate a system which has CXL attached to it, and you can use it like as if it's a system which has a CXL device.
So QEMU has has already
Emulated, yeah.
Emulated
Yeah.
CXL.
Yeah,
Okay.
it's very good in fact.
So what is your take on the amount of support Coherence is going to get in near-term and medium-term CXL systems?
Yeah, I think that's again a very good question. I think from hardware coherence perspective, even though the support is being added in it, and we have global FAM and which is out there where you can use fabric attached memory with multiple nodes, maybe going up to 4096 nodes, I think, as per the spec. But I don't think you will get performance when you really go to hardware sharing between nodes, right? So there are people looking at software coherency also, so where you can turn off hardware coherency and use it, have only the application handle that, saying that only one writer at a time and maybe multiple readers or something like that. So depends on how the applications will use it.
Any additional questions, folks?
I think probably it was not explicit, but I think this is it won't performance will be lower compared to NVLink, right?
Yes, it is. So today it is same as PCIe, what PCIe can support. So it can go up to, you saw 256 gigabytes per second and things like that. So it's not like the 900 gigabytes per second or the 1800 gigabytes per second or something. You see like almost 7x numbers with NVLink, I think.
Yeah.
So that's a challenge which the spec has been working towards. But they've also been trying to see that the use cases are slightly different. This is more of memory semantic fabric. This is more memory attaching more memory to a system. So that's kind of the use case which they are going after, rather than NVLink, which is more GPU focused and GPU being able to access.
But my actual question was can something be exploited from GPU side, meaning doing a DMA to a normal PCI to the post RAM compared to traditional DIMM? Would this work out faster?
It would. In fact, that's where I would have thought that the Type 2 would take off more, because you can actually even cache with this. But it is something I think NVIDIA has probably started thinking about it, because they've started adding more Type 2 maturity into the specification going forward. So maybe they are thinking about it going forwards. But right now there are almost no people using GPU except Panamnesia and a few of the Korean companies, I think.
Thank you.
Alright, if that's it, let's thank our speaker.
Thank you.
I'm supposed to pass this to you.
Yeah.
Yeah, go ahead. Alright, so the next speaker is Dr. Biswabandhan Panda from IIT Mumbai. And I was informed that he's the latest rock star of microarchitecture in India and abroad. He has multiple great papers on microarchitectural innovations, and he's going to talk about sort of lower level, going all the way down in the abstraction to the memory hierarchy of CPUs and the microarchitecture of these systems. And so I will welcome Biswa to give the talk.
Okay, can all of you hear me? Yes? Okay. So thanks Murli for the rocking introduction. How many of you are feeling sleepy? Including me, right? So thanks to Arka, Sumit, CSA, IISc for awesome air conditioning and awesome food. So let's clap for them. And this is just an attempt to make sure that I won't be feeling sleepy for next half an hour, okay? So what I'll be talking about for next half an hour is microarchitecture stuff. That's what I've been doing from last K number of years. And with a focus on many core servers. Okay. Typical disclaimer that are part of all the talks that I've been giving from last few years. You can just read it loud, right? The final thing is actually important. Why are you talking about CPU and not even GPU? Right? It's okay if you're not talking about AI, LLM, and ML, but at least talk about GPUs, right? Yeah, GPUs are good. But so I will use this image from Mark. So this is from IISc 2018. Murli was actually the general chair. And so this was an image adapted from his slides from one of the security panel, right? And he made a statement few hours ago. This is October 30, 2025, right? So everything is important. LLM is indeed important. GPU performance is important. But CPU performance is extremely important. And you should read that statement along with this figure. Okay, so to all the students in this audience, so whatever you want to do it, but don't forget CPUs. Okay, so with that, I will jump into the real problem at hand. So we will look into server CPUs, which are kind of bread and butter for all the modern workloads that you can think about. They run non-stop, 7 days a week, 30 days a month, 365 days a year. And these workloads are different from the kind of workload that we run in our, traditional, conventional computing stack, right? Like desktop workload, running a simple compiler or some, basic software, right? And so what I will do is I will go deep into the server and try to see what exactly they have. So these are CPU-based servers, so definitely they have CPUs, right? And now what we will do, we will go inside the CPUs. Of course, there are tons of DRAMs. But the way the core count is growing, this guy is actually not able to pump data at the same rate that these guys are demanding. So there's a problem of bandwidth that all of us have been discussing from the morning. And typical latency problem is there anyway, right? So for every request this guy sent to this guy is slow, so it will take time, right? Okay, so my talk will be divided into two parts. In the first part, I'll actually talk about even conventional workloads running on a server system. How do they look like in a modern or even conventional memory hierarchy with multiple levels of cache and DRAM? This part of the slide is actually for data. This is for code. So if you're familiar with architecture community, so you must be familiar with workloads like spec benchmarks. So if you compare spec benchmarks with recent server workloads, you will see one difference, which is that the number of instructions coming to last level cache is kind of high. Okay, what it means that for server workloads, the code footprint is actually in MBs, which means they are not fitting into your small L1I cache, not even into L2 cache, and the instructions are now coming into last level cache, which is a new thing for microarchitecture community, because so far we have been bogged down by data. Data is actually the problem. I should make sure my latency for data is always low, right? Why it happens? Because you have multiple layers of system stack, libraries, runtime systems, and whatnot. That makes it extremely complicated, and the control flow jumps here and there, along with the huge code footprint, right? Okay, so I'll bring something from Krishna's talk, right? The grandpa that Krishna mentioned a few hours ago, right? And he just kept on adding cores. I won't do that in this talk, okay? Instead, I will actually focus on single thread, which is part of a multi-threaded program, but finally at the end of the day, I will focus on the latency of a single thread, right? And why is it? So this is actually Amdal. This is not the grandpa that Krishna mentioned, okay? And for whatever reasons, the grandpa actually forgot the Amdal's law, but thanks to all my lectures at IIT Madras, so I still remember Amdahl's law, right? So I'll stick to Amdahl's law, right? Because finally your parallel programming performance is limited by single thread, as simple as that. Okay. So with all the background, now let's jump into two kinds of workloads that we can run on server machines. Conventional workloads which are mostly data dominated, right? But code footprint is pretty low, so which means the L1I cache hit rate will be almost 100%. And then the new server workloads where this is bottlenecked by both data and code. Okay. So let's start with the first part. So I will move into multi-core now from single core. And what you can see here is there are like 32 core system, each having their own private caches, both for data and instruction. There is L2 cache shared by both this data and instruction cache. And there is a mega last level cache shared by all the cores, right? And what is interesting here is, all these caches, they take few cycles, tens of cycles, maybe close to 50, 60 cycles. The moment you cross this boundary, you start hitting DRAM and you start paying the costly DRAM latency, okay? So this is something from Google's web search workload, where they actually distributed the entire cycle that this web search spent on an Intel Xeon server. And so there are many semantics here, so I'll try to keep it short. This part of the pie chart is actually all good. The CPU is actually retiring instructions at a rate which was expected it to retire. The problem is actually coming from this guy, the green guy. Although it's green, it's actually a problem, right? And you can look at this too, right? So this part is actually for data. The processor is actually waiting for data, and this part is actually for instructions, right? So if I combine all this too, so I'm actually spending almost 45% of my cycles waiting for either data or instructions, right? So this is the summary. But first I will focus on the data part because that's easy to understand. All of us have written programs, we demand use data structures, right? And so we will try to amortize that latency first. Questions, okay?
Ignoring batch speculation.
It's there.
3.4%.
Yeah, it's there, but that's not part of my memory hierarchy. I have to come up with a better branch predictor and take care of that, right? So my focus in this talk is only about the memory hierarchy, keeping both code and data. Okay. Right, so what we'll do for next few minutes, we'll actually play a game of latency and bandwidth, right? Keeping both data and instructions. So the things that matter here is cycles. Every cycle matters. At the end of the day, the number of cycles you save eventually will give you performance improvement for a single thread. And if you have a multi-core system, hopefully it will actually have a linear increase in performance improvement, right? So I will be talking about two works, one that appeared in Micro just last week, and one that will appear next year in ASPLOS. This is work done by Shweta, who is here. And this is, the other part is done by Vedant, who is also here. So they are presenting posters, so go and meet them after the talk. So let's start with the problem, right? So we have core, multi-levels of cache, and once you cross the last level of cache, you have to pay the penalty, okay? So what's the solution? Make sure that you get your data in one of these cache levels, right? Do whatever you want. So that's what the microarchitecture community has been doing. You try hard to make sure that you don't go to DRAM frequently. One simple way to make sure that you don't go to DRAM frequently is you decide which addresses you should keep in your last level cache, right? And typical policies, what are called the replacement policies, they actually decide, okay, which one should I kick out, which one should I preserve, based on some heuristics, which is typically known as the reuse behavior. So whether an address will be reused in the future, based on that, you come up with heuristics and decide whether I should keep it in my cache or not, right? So a 50,000 feet view, let's say this is one of the cache set, these are the addresses. Now a new address is coming from DRAM. Now I need to decide whether I should keep it in my cache for longer duration or for a short duration, right? So what I will do, if my heuristic says that it will be cache friendly workload with high reuse, I'll try to keep it with high priority so that the replacement policy won't kick me out. On the other hand, if this is actually not going to provide any reuse, then I will make sure that it gets kicked out pretty easily, right? Like in the very next miss, right? And there are tons of techniques proposed in last 2 decades, and most of these techniques actually decide these priorities when the line or when the address enters into cache. This is called insertion-based policy, right? When you are inserting, you decide where to keep your inserting cache lines. Okay. So this is nothing new. It's actually almost 18 years of research in architecture community, right? And I'm not trying to push the performance limits of all these techniques. I'm not good at that also, right? The takeaway, sorry, did I miss something? Yeah. So this is one of the state-of-the-art replacement policy, which appeared a few years ago. But after that also there are a few ML and RL techniques that appear. I haven't put it here. Just putting ideas which are a bit of microarchitecture, although there is a perceptron that you can see, right? And this idea, what it does, it actually uses signatures to predict the reuse behavior of cache lines, okay? And signatures are nothing but program counters. So the heuristic here is addresses brought by a PC actually provide all the addresses brought by a single PC behave similarly. So you can actually track your reuse behavior based on a program counter and not based on address. And at the end of the day, all the addresses brought by PC, either you tell them cache friendly or cache hours. Right? So it's kind of a coarse-grained way of classifying your cache lines. So if I have a cache of, let's say, 2 MB, 2048 sets, what I do, I actually select few sets, which is called a sample cache. It's a well-established idea in our community. And these sets will actually be used to understand the reuse behavior for these PCs or these program counters, right? And based on the reuse behavior, you decide whether this PC is cache friendly, green meaning it's friendly, red meaning it's actually not friendly, right? There are other semantics. I don't think we need to be worried about that. Just keep the bigger picture in mind. There's a sample cache, there is a predictor that predicts the reuse behavior of a PC, right? And so these are the metrics that community has been using. It is called estimated time remaining. Lower is better, which means it will be reused frequently, and if it is higher, it means it won't get a reuse in the near future, right? Okay, so all good. This idea is supposed to be closer to Belady. So Belady's replacement policy is the ideal policy which appeared in 1960s, and the community assumed that okay, all done, right? We are good with the cache replacement policy. Time to stop working on that. But then what we started seeing is no one is looking at all these ideas in a many core system, okay? And the way it should be evaluated. Okay, I will spell it out what exactly I mean. So you can see here there are multiple cores, and this is a large monolithic last level cache, right? So if you have a 32 core here, you will assume it's a 64 MB last level cache sitting shared by all, okay? But none of the papers actually do what they are supposed to do, which is the last level cache is actually sliced. It's not a large 64 MB cache. It's actually 32 2 MB cache scattered across interconnect, okay? So the way it works, it is still shared. All the cores can actually access it, but they have to pay some penalty in the form of interconnect. So this is the new thing that I just added, right? And each slice which is closer to a particular core is called local slice, and slices which are a bit far away, they are like remote slices, right? And now what's the problem, right? If I think about all the policies that people have proposed, you have sample cache per slice now, instead of having a big sample cache. And now you have predictors. You can say, okay, to make it robust, I will have per core predictors per slice. So if you have a 32 core system, for a LLC slice 0, I will have 32 predictors here. So they will actually learn for each of their cores independently, right? Let's look at the problem here. The problem here is each slice actually using its own sample cache, all good, and they are using their own predictor. And now we started asking, is this the way we should actually learn or train our reuse behavior, right? So let's look at an access pattern. Let's say core 30 sends request from a particular instruction. These are the addresses. The addresses are getting scattered across slices, right? This is done just to get more and more bandwidth. That's the idea here. And what now will happen is each of this slice will actually start learning the reuse behavior for this guy based on their respective sample cache and based on the predictor that sees their local sample cache. Okay? So then what will happen? Each of these predictors will actually look at accesses from core 30 as AD, GH or EF, but not all. So whatever reuse, training or learning you want to do, it's now local to each of these slices, right? And finally, what you end up doing for this slice, if you want to come up with a replacement policy, you stick to the access which is visible only to this slice, which is kind of a local view, okay? And you can ask if it's okay, right? But what's the big deal? You know, I'm seeing whatever I'm seeing, and based on that, I will decide whether to keep it or not, right? Ideally, like theoretically, right? If you assume this is my last level cache which is shared, my cache should be able to see all the accesses, irrespective of particular slice or particular sample cache, right? Let's see what exactly a Belady will do, right? Because that's the sacrosanct policy that anyone can come up with. Y-axis shows the reuse predicted values or ETR values. X-axis shows the core ID here. And this is for a particular PC from a particular workload called Jalan. If you look at the values here, like for global view, which means if you can see all the accesses across all slices, these are the values that you see. And the Oracle view is what is called the Belady view. You assume that you know everything about all accesses across all slices and try to see. And then finally, it's the mode of the local view, which says what are the most frequent values that you see, right? So if you look at the trend here, the global view is actually closer to the Oracle view in 13 out of 16 cores. Okay? And local view is actually a bit far away from the global view or the Belady view, right? So which means there is still opportunity which people haven't tried out to improve on. But yeah, performance improvement was already there. So that's why this problem was never considered as a problem, right? So the conclusion or the takeaway from this slide is the local view is actually a myopic view. We are not looking at all the accesses across all the PCs, and because of which your reuse predictions is actually myopic. Okay? Okay, so the first thing that we do, we proposed Drishti with first announcement, which is called, you come up with organization where you have global predictor, but which is per core. Okay, again, questions, sure.
So how much is the loss?
I'm coming to that, yeah. That's a good question, but I will come slowly, right? So what we do is the following. So now we have this last level cache, there's the interconnect, there's a sample cache. So now what we did, every core has one predictor, but this is global, which means all sample caches can actually communicate to this guy's predictor through this interconnect, so that this guy can see the global view and will be able to decide which lines to present, right? All good. If you can just do that, then everything is solved. So whatever loads that you will get, now loads will actually traverse to a particular core's predictor. In this case, it's core 30, right? All the PC and the predictions, they also need to travel the interconnect, right? And finally, you will get the best view, right? Okay. So all good. It looks like the problem is solved, right? We should actually wrap up, and I should start talking about the other side of the talk. But the problem is this. If I want to see a global view, forget about improvement. I will start seeing slowdown. And as the cores increase, the slowdown increase, which is intuitive because you are spending most of the time in the interconnect, right? So when we started digging deep into the 32 core, we started looking into, we started throwing latency numbers, like which kind of latency numbers are actually causing slowdown. So on average, we found that around 20 cycles is actually spent on a 32 core system, sending all this PC and ETR values which are used for learning, right? So forget about improvement. At this point, you should say, don't do anything, continue with your local myopic view. At least you will get some performance, right? But thanks to work that appeared from Georgia Tech in Micro 18, they had an interconnect called Knockstar. It's not a typical interconnect like mesh and ring. And this interconnect is pretty lightweight with pretty fast latency, where one guy can communicate with the other guy with 1 or 2 cycles. Okay, so we went to this interconnect and we started thinking, how can we use this interconnect in our setup So now we have a slice, we have a sample cache and a predictor. And now this interconnect, what it does, it provides switches and arbiters, right? So every slice will have a switch and an arbiter, and they will communicate directly. There are no multiple hops. So all the mesh and other interconnect, they get latency because of multiple hops, okay? And that's the reason why we chose Nockstar. Otherwise, we are struggling to find out a way in which we can actually coordinate all of them, right? So this is how it looks. So now if there are two slices they want to communicate, the request will actually go through the arbiter, and it will go to the other slice arbiter and eventually to the switch, right? So this is how we use this interconnect. But you can say, okay, even the latency will be still there because you are using a new interconnect. So the good thing about this idea is we are not using all the cache for learning. We are just using few sets for learning, right? So this learning is different from machine learning, just to put a disclaimer, right? So we are trying to understand the reuse behavior, but for a few sets, right? So this traffic is only for few sets. So whenever requests come to those sets, then only you send traffic in that interconnect. Okay. So the next thing that we observe when you have multi-core systems across multiple slices, we see two kinds of workload. The left-hand side, you can see different sets having different misses per kilo accesses. So every 1,000 accesses that you make, how many misses you see, okay? If you look at this workload from spec, it's a streaming workload. You are seeing a flat behavior across all sets, all slices, which means any set is used for sample cache is good enough that you are using for your learning. But here it's not. It may happen that you will end up using some of the sets which are underutilized, and they will affect your reuse prediction and learning, right? So that's the takeaway here, that the sample cache is underutilized. So what we did, we said, okay, instead of using the sample cache that the community has been using, what happens if we use sets which are showing high misses per kilo accesses, right? The performance suits up. It's again intuitive, obvious, right? Because they are getting the accesses, they are representative, so you should use it for sample cache. So low one, if you see, there's a gap of almost 7-8%, right? So what we did again, simple idea, how to select sets for sample cache dynamically. So you have your sets, you put a few counters here, pretty lightweight, and track their misses for kilo accesses. And once in an interval, you try to replace your sample cache with sets which are actually getting all these accesses, so that you know that these are the sets who will eventually decide your reuse prediction. Right? Okay, so finally, this is the idea. This is sliced cache. You used your dynamic sample cache by finding out the high misses per kilo access, and that's getting populated dynamically. And at the same time, you have a per core yet global predictor thanks to the new interconnect called Nockstar, right? So with that, I'll jump into some numbers. So we actually simulated a Intel Sonikov kind of processor with up to 64 cores, and these are the performance numbers. I'll actually make it quick in the interest of time. So you can see this is the geomean. You see in 4 core, there's hardly an improvement because this is useless. The moment you go to 32 core, the improvement improves. Okay, so and if you go for more and more cores within a socket, you will actually see more benefit. But this is not for a small multi-core system, right? Just to highlight the utility of each of these ideas across different spec and gap workloads. Both the ideas have their own utility, but they work pretty well synergistically when you put them together. Okay. I use the state-of-the-art cache management technique, but this idea is applicable to almost all the techniques that are proposed in the last 15-20 years, because everyone is using sample cache, everyone is using reuse-based predictor using program counters. Okay, so this is something that actually gave me a kick last week. So this is actually from the session chair at Micro. Just after the talk, this is the statement that the session chair made, right? This idea is extremely simple that anyone can actually do, but no one actually did it, right? Okay, so questions, I have already taken 2 questions, so I'll take 2 minutes from the questions, and I'll just jump to the front end part. But I will go at a 50,000 feet view because this is still, it is coming in a few months. So now the focus is on the instructions and not the data. So what modern processors do, they use what is called a decoupled front end, where instructions actually move, or the branch predictor actually looks at instructions way ahead in time, and then eventually these instructions go to your L1 ICAS. Okay, so the L1 ICAS actually sees instructions later compared to the branch prediction, right? And there's a simple prefetching technique that is used called fetch-directed prefetching technique, which just looks at this queue and then start fetching instructions from outer levels of chaos into L1I. Okay, this is to hide the code latency, right? So now, what's the problem? The problem in all these server workloads is you have a pretty high width superscalar processor, which is coming into your fetch stage. But if you get misses in your one of these L1I, L2, L3 for your instructions, it may happen that you won't have anything to decode, right? Forget about rest of the execution and memory stages. Your pipeline is actually rest in peace, right? What's the solution? You should actually try to make sure that your processor never enter into a stage where decode queue is empty, right? So there's a paper that came in IISc 23 that actually tries to do what I just suggested. It tries to find out instructions lines which lead to this starvation of the decode queue and try to preserve them at the L1I and L2, right? So that this decode starvation won't happen. So this is a high-level idea. In the interest of time, I'll just go quick. So what we did, we actually started looking into that idea, and we started finding, okay, if a particular instruction is critical, is it critical all the time, or there is a ping-pong behavior that you see? Sometimes it's critical, sometimes it's not. And if you look at this particular chart, most of the instructions are actually called D-critical, which is dynamic critical, which means once it is critical, it's not that the case that it's always be critical, right? So, which means there is still opportunity for us to improve this behavior. And what we found out, that the control flow of the program itself affects the criticality. So the same PC, if you have a different control path, you find it is causing decode starvation, but if it is going through a different path, it's not, okay? And we use this idea, this is actually the 10,000 feet view. You have 3 different code blocks here. This guy is coming to this function after 10 to the power 6 instruction, but this guy is coming after 10 to the power 4 instructions, right? So in this case, you will see that the reuse behavior is different as compared to this particular case, right? So we just exploited it. We used branch history along with the decode starvation to find out criticality behavior, and it improved performance here and there. But once we implemented this, and we are kind of excited that it will improve everywhere, but we started seeing degradation. Forget about improvement. And the reasoning for that is we are not looking into reuse along with the criticality. And in the interest of time, I'll just jump into this thing. This is the final idea. What we did is we divided all the instruction lines into 4 bins. Critical based on decode starvation, reuse whether you are getting a hit in your cache, and based on that you kind of try to prioritize critical lines, and for each of these bins you kind of create a watermark. Your goal is to make sure that these lines are actually preserved or locked in your cache, which are critical and which are likely to reuse. And you kick out all these non-critical, non-reused ones, right? That's the idea, that's it. And with this is the performance improvement that we got. In some workloads like gigantic improvement, but more or less the average is pretty low, like almost 5%, but it's pretty huge for microarchitecture community. Okay, so that I'm kind of done. So this is the summary. We talked about the back end and the front end, dealing with back end bottleneck and front end bottleneck, looking into the memory hierarchy and cache hierarchy, and trying to improve the latency and bandwidth, right? So these are the things that my students have done, and all of them are here for posters, which is starting in few minutes, right? So go and meet them and ask more questions. There are many other things that we did in last few years. All of them are microarchitecture ideas, both for performance and security. If you are interested, go and look at that. And finally, this is my group. All of them are interested in microarchitecture for whatever reasons. Right? Okay, with that, thanks to all the sponsors who have been supporting this research, and macro thanks for all of you. I think we have time for questions, right? Yeah, okay.
Any questions, folks?
for such a great talk. So my question was on the Drishti part. So when it is optimal, we all know that it works for single core, right? For multi-core, we don't have any kind of that benchmark. So the second missed observation which you mentioned, right?
The dynamic
sample set. So what kind of improvement you guys observe when it is applied for single core, right?
I think the workloads that I saw, right, for MCF you will get the improvement even in single core, right? But for workloads like LBM, you won't get even 0.1%. It's already doing what it's supposed to do. Right?
Yeah, thank you.
Additional questions, folks? So I have a quick question. Yeah.
Great talk. So what's the hardware cost for adding additional connections, right?
The interconnect. Yeah, it's pretty lightweight. Not only in terms of area, but in terms of energy, power, and other trade-offs, right? I didn't talk about that, but the paper talks about everything, and we are actually within ISO storage, ISO area, ISO power, right?
Another question I have is like you gave an example of MCF or like LBM, right? And then spec is like it's the same kind of workloads run across all 32 cores. But in the actual data center, that may not
they are
be
heterogeneous.
right?
Yes.
Heterogeneous.
Yeah.
So is your did you try with this heterogeneous workload?
Yeah. So one of the plots had both heterogeneous and homogeneous workloads, right? So homogeneous we use so that it will stress your memory bandwidth highly, right? In heterogeneous you have some friendly, some unfriendly workloads, but we have plots and results for both. Yeah.
Nice talk. So, in the Drishti part, you were mentioning about the problem of uneven distribution of accesses, right? So, are you using?
No. It's not uneven distribution of accesses. It's uneven distribution of PC getting scattered across slices.
Yeah, but when you apply for such, okay, so it's not about just the distribution that you are monitoring for the monitoring sets.
Yeah.
Okay.
Just I have a quick question. So, one of the things that you mentioned is that you lack global view, and if you want to capture the global view, you have to do a lot of data across the network.
Yes.
But can you actually sample the global view itself? In other words, use fewer of those transactions to construct the global view, and then you don't need to have such a large new network just for this traffic.
Yeah. That's an awesome point. In fact, that was one of the reviews which actually suggested that can you actually solve this problem without adding an interconnect, right?
I did not review the paper, but
yeah. Anyway, yeah, that's a pertinent point. Yeah.
All right. I guess we have one last question. 1 minute left. So.
Hey, Hari, you are not supposed to ask questions.
Instruction lines are more costly in terms of misses than data lines, right?
Not really. It depends.
Then my question isn't really valid.
Good.
All right. With that, let's thank our speaker. Sorry, supposed to take this with you. All right, so the next speaker is Arun Ramachandran from AMD. Once people settle down, I will. So Arun has been with AMD for 17 years, and he works on a variety of topics related to LLM memory systems, and I have actually had the great pleasure of actually working with him on a couple of the papers recently, and I greatly appreciate the kind of deep memory knowledge he brings to the LLM frameworks, and so I think he will I look forward to him talking about the LLM opportunities, particularly in the context of AMDs.
Yeah, thank you, Professor, for the kind introduction. I'm thankful for this opportunity, and today I will be talking on LLM inference system, particularly the LLM opportunities and the AMD MA roadmap. So particularly, most of this work I've been working under the guidance of Professor Govind out here, and yeah, I'm thankful for the opportunity to be collaborating with Professor Murli too. Thank you. So the agenda of today's talk is, we'll get started with the AMD IISc collaboration. So from the industry side, I'm advised by Prakash Raghavendra, and so I'm deeply working towards some of these activities specific to KV cache management. So I'm guided by Professor Govind. So the second part of the talk, we'll be going over the AMD MI roadmap. So as a part of IISc AMD Hack initiative, AMD EPIC processors, Instinct GPUs and Albio accelerators are installed in Indian Institute of Science. There has been a lot of activities specifically on LLM inferencing on CPUs, FPGAs, ML input processing pipelines and data frame design. Particularly the one that we'll be focusing on is on the efficient LLM inferencing on the CPUs. So just before we get started, I know actually Professor Murli has said a lot of the context. The one terminology that I'll be using over this presentation is KV cache. So I'll just set context of what KV cache is. Large language models typically have two phases, the prefill phase and the decode phase. During the prefill phase, the input text is being processed and the attention states are being cached. During the decode phase, one token is getting generated at a time and these cached attention states are being reused. So this attention state is the key value cache, and the key value cache is generated during the prefill stage and it incrementally grows over the decode stage as more and more tokens are generated. With that context, I'll get started into the evolving landscape of LLM serving systems. In the interest of time, I will handpick just few of the areas that have been evolving. Traditional large language models were typically text-based, but modern architectures support audio, video and others in addition to text. If we just pick batching as one of the areas. Classically, a large language model used fixed size batching schemes. A long running prompt could incur a lot of tail end latency, thereby it should wait, the next set of batches should wait until the current batch is complete. But with techniques like continuous batching, batching could happen between the decode tokens. Modern inference serving systems support efficient scheduling schemes that can interleave compute heavy prefill requests along with decode heavy tasks. So this results in mixed batching. Modern LLM serving systems are also exploring disaggregation, where distinct resources are allocated based on their workload profiles. If we just take compression as an area, so traditionally parameter pruning has been the area of focus. Basically it is pruning heads as well as dimensionality. But as context set today, the context size of the large language models continue to increase. Today we have 32,000 tokens being supported, or large language supporting up to a context of millions of tokens. So thereby bounding the size of this KV cache becomes significantly important for system performance. And to bound that, tokens needs to be evicted, and this is as a result one of the surging areas has been token pruning. If we just pick kernel as one of the evolving areas, there has been a lot of custom kernels developed. Today we had a talk about sparse kernels, sparse attention that requires development of custom sparse kernels. There have also been kernels inspired by OS virtual paging policies, which is referred to as the paged attention kernels that reduce fragmentation within the KV cache blocks. Flash attentions are another variations of custom kernels that enable deeper fusions, and their blocking strategies reduce the accesses to the HBMs. With this context, we will just quickly get into the problem statement that we have been collaborating and working with Professor Govind and Professor Murli. So despite extensive optimizations done in the LLM inferencing space, we still see a lot of headroom for further optimization. Specifically in this talk, we will be looking into the KV cache management and more specifically into the KV eviction policies as well as the KV insertion policies. As you see in this slide, large language models go through a sequence of layers to decode a token. And today, the frontier scale models, right, if you have to build a larger model, the simplistic view of it is if you increase the layers and increase the hidden dimension, as you see by the scaling law, the number of parameters continue to explode. And each layer consists of the attention and MLP block, and for our discussion, attention is something that we'll be exploring in greater detail. So this attention computation depends upon the query vector that basically is multiplied with the key cache, which is the attention state. Now that results in attention scores, and these attention scores are normalized to get attention weights. And now these attention weights are multiplied by the value, which is again an attention state, to get the attention output. But what is most important is the attention is a function of KV cache. So it basically, as Professor Murali pointed out, actually you try to figure out those important tokens that contribute to the attention output, and now KV cache maintains the attention state of the context of the tokens decoded so far. Now if we just look into what happens during an autoregressive decode, as and when tokens are being decoded, the K and the V cache starts getting updated. Now, why is it a big problem? As the sequence length continues to grow, which is a challenge with today's LLM with millions of token context, or as the batch size continues to grow to exploit the compute efficiency, the KV cache size significantly grows higher in size. And now, a lot of some of the areas of research have focused towards bounding this KV cache size. And now, bounding this KV cache size to a fixed budget has resulted in emergence of token pruning. There has been several techniques, state-of-the-art works such as steaming LLM and heavy hitters that predominantly focus on fixing or bounding this budget. Thereby, this necessitates KV cache eviction. So if I take, for example, steaming LLM, which is one of the popular works, the sync tokens are considered to be important or never evicted. But once we reach this window, the oldest token gets evicted. That results in a hole. And now you'll need to shift all the entries to the left and then append the new token. So the major challenge with this eviction is that the KV cache incurs and shift and append operation, which is linear time. Additionally, every time a token gets evicted, the position index associated with the token also changes. And most modern networks do a specific operation which is called rope, which is rotary position embedding, that is directly a function of position index of the position. So what this means is that in addition to the KV cache shift, we also have an additional shift associated with the rotated K cache, which I will be just skipping out in the interest of time. So what is the motivation, or what is our exact contribution? So our motivation towards this problem is to figure out what happens actually if we replace that shift and append operation with an in-place update operation. So the blue line here shows the overhead that is incurred because of the KV cache shift. Now supposing that we replace that with an in-place operation, we will be in this black line. This is the KV management speed up that we would have ideally got to. We spoke about the second component, which is the rope that comes out of the positional encoding requiring the rope recomputation. We observe that this orange bar shows the time spent in the rope because of the KV cache eviction. Supposing that rope rotation is being done in place, this particular aspect, the speed up could have been significant. So this remains the motivation, we wanted to study actually if an in-place update is really possible. Now we try to see what happens if an in-place update is done. An in-place, as you see actually, the original update of shift and append would have maintained a logical sequence or a logical ordering in a logical ascending order. But because of this in-place update, the order of the KV cache token gets permuted, which actually means in place update leads to permutation of key and value cache along the sequence dimension. We now show that even though the K and V, which is the KV cache, is permuted along the sequence dimension, attention of query, permuted key and permuted value is exactly same as the original attention operation, which means that the shift and append operation could in fact be replaced by an in-place update operation. We take a small example where a query gets multiplied by key. On the right hand side we see the values are getting permuted. The entry 6, 7, it becomes shuffled along the sequence dimension. Supposing that we multiply query with key, it results in attention probabilities. On the other hand, we get the permuted attention probabilities. Now, when we multiply it with the value vector, it results in the attention output, but the permuted attention probabilities multiplied by the permuted value exactly results in the same output. Leveraging this principle, we extended the proposed algorithm and integrated it with Hugging Face, which is one of the frameworks for LLM, as well as VLLM, which is another popular framework. Our observation, what we could observe is that because our in-place update method unifies eviction and insertion into a single operation, it seamlessly works across the complete stack, regardless of the models that are being used, regardless of the algorithm. If a steaming LLM algorithm with UPIS could be compatible with Hugging Face, while an H2O algorithm with UPIS could be compatible with VLLM, thereby ensuring a two-way compatibility. We now look into some of the results that we achieved as a part of the UPIS work. So the baseline here corresponds to the steaming LLM, that is shown as 1.0, but when we move to random eviction schemes like heavy hitters that incur a higher penalty because of the gather operations, we show that steaming LLM applied over UPIS and applied over H2O, they are still significantly better than the baseline. And now we observe we show strong scalability across different models and sequence length. Next, we extend our results to GPUs. These are MI210 GPUs, where we try extending the sequence length from 2048 to 8192, and we still observe a significant gain of 1.73x. We integrate our solution with page attention, and we compare it against the autoregressive page attention, and we observe a speed up to maximum of 7x. In summary, we unified the KV eviction and insertion into a single operation that reduces the shift and append cost associated with the KV cache management, and then we have integrated our solution into steaming LLM and heavy hitters to popular state-of-the-art works, and then we show a full stack compatibility with our solution. Next, we'll move on to another interesting problem which comes up with the KV cache insertion. As autoregressive models decode tokens, the KV cache gets incrementally updated. And now, the layout for KV cache has been an active area of study, while some of the techniques like the Hugging Face and some of the frameworks make use of virtually contiguous memory. Some of them make use of indirect KV management. Both have its own advantages and disadvantages. The virtually contiguous memory brings in performance challenges, which we'll be going over the next few slides, whereas the page attention based kernels have scaling challenges, and because they will need custom kernels need to be developed for this. So here we'll start with a KV dynamic scheme, which is every time a token gets generated, we allocate an incremental memory, and the orange bar here shows the insertion operation as a part of this KV cache. But what this insertion operation leads to is an increase in the amount of copies, as you see in the diagram below. So the KV dynamic policy incurs a memory allocation cost as well as the copy cost that comes up for every incremental allocation. The other commonly used method is an upfront allocation strategy. So you allocate the complete memory ahead of time, but the challenge with this approach is the gray bar that is shown here, they all become zeros, they become redundant compute. So you allocate a bigger chunk of memory that enables the KV cache insertion shown in orange to happen in place, but you have way too many number of redundant computation. So as a part of this work, our motivation was to find, is there a real balance actually that we could achieve where both the attention operation as well as the KV cache operations are minimized. So the x-axis here shows the number of allocations on a log scale, and now if we plot actually the KV cache operations, they are significant when the number of allocation is just 1. The SDP attention operations is significant because of the redundant compute when the allocations is 1. On the other hand, the KV cache operation is significantly higher. The blue bar that shows when you do allocation incrementally. But is there a middle ground or a sweet spot that we could find that maximizes the tokens per second while reducing the KV cache size operation as well as the update operation? So we, as a part of our proposed solution, we build an analytical model and figure out that the optimal allocation policy lies somewhere at about square root of n, where n remains to be the optimal context size. So if the context size of the model is 1024, the optimal n remains somewhere is proportional to 32. We now validate the correctness of our our solution with the correctness of the analytical model across different model sizes starting from opt 2.7, 6.7 and 66b, and we observe that roughly at proportional to square root of n, we see the normalized latency to be coming down. As we the graph below shows, as we increase the number of allocations by a factor of 4, the optimal allocations shift by a factor of 2, which implies that the analytical model holds true. So even though BMC achieves optimal allocations at square root of n, it still has some redundant compute. This is where we took Professor Murali guided us actually with the speculative decoding approach. With speculative decoding, the draft models generate multiple tokens and the target model accepts, the target model verifies the correctness of the tokens and it accepts the tokens generated by the draft model which are correct and squashes the others which are not correct. The big advantage of speculative decoding is it removes the sequential dependency that we have with the autoregressive mode. That's one. Second, the autoregressive mode is memory bound because the general matrix vector multiplication is converted into matrix multiplication, so it becomes compute bound. So the idea we had here is actually to convert some of the wasteful computes, zeros, that could be repurposed with the help of speculative decoding to more meaningful compute. So this is a representation of the KV tensor where we have the batch dimension on one side, hidden dimension on the other area, an in-place update that is happening at T8, efficient repurposing that is being done between T9 and T15 leveraging speculative decoding. The unused KV tensors becomes the padding. Then we have a bias fuse technique that recovers the accuracy back. All these operations together are implemented in a single blast operation which corresponds to the query and key multiplication. So here we compare the performance of BMC against Hugging Face, paged attention and Microsoft Deep Speed. At a geo-mean level, we observe that we are roughly at about 3.27 times over Hugging Face at an end-to-end inference level and better than VLNM and Deep Speed by about roughly 1.4x. With speculative decoding, we get a performance uplift of 1.5x to 2x over the autoregressive model, and in addition to the gains from the autoregressive model, BMC provides an additional uplift of 1.1 to 1.2x. So far, we reviewed two solutions based on the KV cache management schemes: unification of eviction and insertion into a single UPIS update that enabled a full stack solution. Second, improvement with KV insertion policies with the help of BMC and speculative decoding. So these are the two works that I pursued under the guidance of Professor Govind. Now we'll move ahead quickly on to the AMD-MI roadmap. So with a lot of evolution in large language models, distributed LLM inference becomes of significant importance, and that requires an efficient software stack. So AMD's ROCm stack is extended to integrate LLMD, which is a state-of-the-art distributed inferencing serving system, and it enables important features like disaggregation, where the prefill and decode phase having distinct characteristics, they are allotted distinct nodes or distinct resources. A lot of the model LLM architectures make use of MOEs, which are mixture of experts, where the expert weights are shared across the GPUs. Now all this requires is an all-to-all communication across the GPUs. And now this communication happens via the ROCm RCCL, ROCm collective libraries, that ensures the all-to-all communication and ensures the results are processed back to the originating node post the processing is done. With the hardware capabilities, ROCm stack also ensures support for FP8, FP6, FP4 and mixed precision. Now we'll get to an end-to-end view of the MI roadmap of AMD. So AMD makes use of Pensando DPUs as the front end. This is predominantly to ensure the security aspects. So given a number of requests are coming, Pensando helps identify the malformed requests as well as the non-AI requests, filters out them, and then feeds only the right requests to the AMD EPIC CPUs. The AMD EPIC CPUs will be acting as orchestrators, and to orchestrate, it does the job of pre-processing, tokenizing, as well as batching the right request and then feeding it to the GPUs. With frontier scale models and techniques like MOE that requires weight sharding, we need scale-up networks where hundreds to thousands of GPUs should be part of an rack, and now that requires low latency, high bandwidth communication. AMD is leveraging UAL link for at the rack level, specifically for the all-to-all communication. Modern AI data centers also require gigawatt level scaling, which requires scale-out networks, and now, as Mark pointed out in today's slide, actually, Ultra Ethernet Consortium, where AMD is a part of it. So one of the major advantages of UA Link and the Ultra Ethernet Consortium, they are truly open standard specifications, and UA Link allows the flexibility and interoperability of heterogeneous devices, meaning you could mix and match any of the accelerators within the link. It need not be tied to a specific vendor. As a part of AMD Helios rack solution that will be available by 2026, the AMD Pensando DPUs, AMD EPIC CPUs, AMD Instinct GPUs will be part of the same rack powered by the software solutions from AMD ROCm. In summary, the Helios based architecture, particularly at the gigawatt scale, requires a lot of efficiency. So with advanced processing nodes, specifically reaching to the hexaflop scale, and the memory reaching to several terabytes, will be able to run frontier scale inferencing and training with the Helios rack. With high speed interconnects that require support for modern models, including the MOEs as well as the weight sharding requirement. So we'll be, ROCm software solution will enable to scale the all-to-all communications within the rack level. So with this I take this opportunity to thank the organizers, and I will conclude upon the session. And finally, for students who are interested to try out the Instinct accelerators, they could look into the AMD developer portal that provides free credits for MI300 accelerators. Thank you.
Questions, folks?
Nice talk, thank you. So the first part of the talk, you mentioned you want to maintain contiguity of KV. I assume you're talking about this in virtual memory, right?
Right.
So say for example, you're doing rolling window attention, right? You said you're going to shift and then append the KV to the end.
Right.
So doesn't page attention already give you the capability to compute attention over non-contiguous KV? Why is it a necessity that you have to do this shift and add?
Okay, I'll talk about in detail. VLNM inference track is particularly matured for the KV insert operations that has been already upstreamed, but specifically solutions specifically related to KV evict, specifically for streaming LLM or heavy hitters, they are not still upstreamed into the VLLM. So the KV evict for sliding window is available, but sliding window with attention sync is still not an upstreamed solution into VLLM. Particularly, second challenge that comes up with VLLM is the custom kernels that take a lot of time to get implemented. The third opportunity we see is that when we merge our solution along with speculative decoding, it becomes a natural blast problem where gems tend to outperform non-contiguous memory accesses on CPUs. Yeah.
So is your solution to keep this contiguous or still keep it non-contiguous and do inserts?
Yeah, our solution is to keep it contiguous as a part of KV eviction, and in case of KV insertion, the redundant zeros are being replaced with the help of speculatively decoded tokens. They are repurposed.
Any additional questions? Well, if not, I think we should thank our speaker. Folks, there is that's the end of the session.